Welcome to the Ultralight Airplane Workshop. In this video, we're going to continue working on Dan Raymer's book, Simplified Aircraft Design for Homebuilders. And in Chapter 7, in the structural sizing section, we're going to work on load limits. And as you can see from our little drawing here, we're going to figure out the design speeds and the load limits at those design speeds. We're doing this work for an ultralight airplane we're designing. Now, this ultralight airplane falls underneath the U.S. Federal Aviation Regulations Part 103, and we're calling that airplane the UWS-4. And to extend the information I gave the patrons here in the last video, the patrons earlier got access to what I had called Part 10A, but I've decided to change to Part 10B. As you can see here, we're working on Part 10B, and this is basically redoing that video using a different source for our specifications. And I'll talk more about that here in a moment. Well, we're sticking with tradition in this video, and we're going to review a little bit of what we talked about in the last video. That was Part 10A, the new Part 10A. In that video, we started talking about the materials that we're going to use in the UWS-4 Ultralight airplane. And basically, it's an aluminum airplane. So the skins on the airplane will almost all be aluminum. Ribs are aluminum. The spar is going to be a built-up spar instead of an extruded spar, and it'll be made out of aluminum. I intend to make the flaps a pseudo-slotted type of flap, but we're going to use a piano hinge on this flap, and it's going to be hinged at the bottom skin of the wing. I'm going to use an airfoil that creates a little bit of drag when you deflect it up, and that's supposed to help with adverse yaw. And again, it's going to have a piano hinge, and in this case, it's going to be hinged on the top skin of the wing instead of the bottom skin like on the flap. On the tail, again, it's going to be aluminum, except it's going to use a plain hinge. And the fuselage, I still need to give that more thought. It's probably going to be aluminum, but that part I haven't figured out yet. I'm going to put off just a little while. And something to mention about the aileron, the flaps, and the rotovators. I intend for those to be built up with an aluminum frame covered in fabric. As I mentioned in the intro to this video, we're using Dan Raymer's book, Simplified Aircraft Design for Homebuilders, to help guide us in designing this ultralight airplane. Now, Dan's book is really tailored more toward the light experimental airplanes, and our airplanes are far, far lighter than those. So there are some differences that we're encountering. But Dan's book is a fantastic book because he really did a good job of simplifying the design process, and it's really helped a lot with the UWS-4 design. If you might be interested in Dan's book, there's a link down in the description of this video that will take you to a webpage on the Ultralight Airplane Workshop books webpage. Those books that I like to use. If you click on the link for Dan's book, it'll take you to Amazon. If you buy that book there on Amazon, the Ultralight Airplane Workshop will get a small cut of the proceeds. Since this video is numbered 10B, you might suspect that it's kind of carry on or follow on to 10A, and it is. We're still working on the Analyze It chapter, and we're still on the preliminary structural sizing section in that chapter, and that starts on page 97. Now, this video is going to be very long compared to the amount of time that Dan spent talking about the specification we used to make this video. And that's Part 23. Now, Part 23 is a section of the Federal Aviation Regulations that are used to tell designers how to design an airplane that can be certified by the FAA. Now, Part 23 covers everything from big airliners down to very light airplanes. Well, we're going to slightly adapt and for the most part directly use the specifications that are used for the small airplanes. Now, there's a slight issue with using Part 23 now. Part 23 was changed back in something like 2016 or 2017 so that the guts of it has been pulled out. And now they make vague specifications, and all the information that was in there that was specific has now been moved over into specifications that are controlled by the ASTM. And for light sport airplanes, that is in ASTM F2245. Now, the problem with trying to use ASTM 45 is that it costs money to get it, and they have a very stiff copyright on it. And in fact, I made version 10A of this video using ASTM F2245, and I didn't like the copyright that they had, so I decided to start over. And since you can still get Part 23, the historical version, prior to 2017, we're going to use that. So the main thrust of this video is figuring out load limits for the airplane. And those are loads that can be applied to the airplane without damaging the structure. Now, for the most part, we're talking about limit loads, and that's what I was just talking about. And the way you come up with the limit load is you have your design weight and you multiply it by a load factor. So the load limit, like I said, is the load you can apply on the airplane without damaging it. Now, there's also something called the ultimate load, and that's your load limit multiplied by a safety factor. The ultimate load is where your airplane will probably fail if you go up to that load. Now, in the calculations that we're going to use here, I've got two different weights we're going to use. One is the maximum weight that the airplane will be, and this is going to be all the payload and the airplane added together. I'm still going to use the 517 pounds that I've used all along. And we came up with this 517 pounds in part 2 of the video series of the UWS-4 design. Now, the next weight we're going to use is 419 pounds. Now, I didn't use a specification to come up with this weight. This is what I think will probably the lightest usable weight the airplane will ever probably have, and that would be a pilot of about 150 pounds, the empty weight of the airplane, and half a fuel load. Now keep in mind, using part 103, which is with the standard weight pilot and a fuel load of fuel, that's 474 pounds, but we won't be using that here in this video. Now I mentioned part 23 handles from large airplanes, big airliners, down to small airplanes. And there's different categories for these airplanes. And there's different categories of loads. I'm going to be using the normal category, and the normal category is defined in part 23.3.A.1. And by the way, anywhere in the document you see this little symbol and 23 dot something, that's going to be the section in the historical document from January 1st of 2017, where you can find the accompanying information or the specification that I'm using. But to give a brief idea of what the normal category is, it's an airplane that when it's flying, it can do stalls, it can do lazy eights, chandelles, and steep turns up to 60 degrees. Any other aerobatic maneuvers beyond that, it's not supposed to be able to do. Now, under these assumptions then, we can come up with some load ideas for the airplane. Now, there are other categories. There's utility that can do just a little bit more, and there's aerobatic, which can do just about any aerodynamic maneuver. But the loads for that is much more. Well, first, let's talk about the various speeds that we want to design to. And I'll go from the lowest speed to the highest speed. So this speed, this V sub SO, this is the stalling speed of the airplane when we have our flaps fully deployed. In general, for just about any plane, the definition is more like the landing configuration of the airplane. But for us, we just have flaps, we have fixed gear, so the only difference on the airplane is that our flaps will be deployed, fully deployed. Now for us, our speed isn't really a design speed because this speed is specified for us in part 103. We have to stall at or less 24 knots under certain weight conditions. And basically that's that 474 pounds I just talked about. The next speed is V sub S. It's basically the stalling speed of the airplane with the flaps in their neutral position, not deployed. Or you could also think of it as the minimum controlled flying speed of the airplane when the flaps are retracted. The next step is V sub F. This is going to be the maximum speed that we're going to design the flaps to be able to handle when they're fully deployed. Next is V sub C, that's our cruise speed. V sub H is the maximum level flight speed. And for us, that's specified by the FAA in part 103. So for us, it's not a designed speed, it's specified. The next speed is V sub A, designed maneuvering speed. If you're below V sub A, the airplane will stall before it can have a structural failure if you do all the design correctly. Now at speeds above V sub A, that's where you got to be a little more careful because it's possible to damage the airplane if you exceed the load limits. Below V sub A, that's not an issue. You can't exceed the load limits. The wing will stall first. V sub NE is a never exceed speed. That's not one of our design speeds. That's something that you put on the airspeed indicator for the pilots. But the next actual design speed is V sub D. That's the speed that you design the airplane to be able to dive at. That's maximum speed of the airplane before you start having issues. Well, next, let's start calculating some of our design speeds. Let's work on V sub S and V sub S0. So first, let's do V sub S. And that's our minimum controlled airspeed or the stalling speed when we don't have the flaps deployed. That one's pretty easy. We just used the lift equation. This is just the lift equation rearranged a little bit, and it should look pretty familiar. So we're going to take the square root of everything that's in here. This is the weight of our airplane, the total weight. This is 1/2. This rho is the air density. This is the maximum coefficient lift of the wing, not the airfoil. And this is the surface reference area of the wing, the planform surface area. For V sub S, I'm going to use that maximum weight, 517 pounds. For rho, square density, since I'm using imperial units, that's going to be slugs per cubic feet. We've always been using the surface reference area of 121 square feet. And if you'd like to look at how we figured that out, that's in part 4 of our video series. And the maximum coefficient lift of the wing, we also figured out in part 8. And that's a little over 1.5. And this 2.04, that's with flaps fully deployed. So for V sub S, you plug all this in and we get 28.6 knots. So next is V sub S0. Now that's using this 2.04 that we just talked about. And that's with flaps fully deployed. Now remember when we did our calculations for part 103, we used 474 pounds, and that gave us 24 knots, which is what our FAA regulations require. But for this flight envelope calculation, I want to use the maximum gross weight of the airplane. That's our 517 pounds, and you plug all that in, and we get 24.9 knots. So that's only an extra knot for stall speed. That's not too bad. For our next set of design speeds, we're going to figure out the maximum speed we can have our flaps deployed. We're going to figure out our cruise speed, and we're going to figure out our dive speed. Now in this case, it's not equations like our lift equation, and we're using directly part 23 to figure this out. Now using part 23, for our flap speed, we either take V sub S multiplied by 1.4 or our V sub SO multiplied by 1.8, whichever is bigger. And that's supposed to be our V sub F. And that turns out to be 44 knots, which is pretty high. That's almost up to where our normal cruising speed would be. I think we could probably reduce this value if we wanted to, but I think we'll leave it here for now. Now part 23 has two ways of calculating the cruise speed. They have a minimum cruise speed and a maximum cruise speed. And for us, they kind of get flipped around, which is kind of interesting. So let's look at the minimum cruise speed first. And it's this equation right here. You just take the wing loading, which is the weight of the airplane divided by the surface area, and I've got that calculated here. You just take the square root of that and multiply by this 33 factor. Now for us, that turned out to be 68 knots. But then in another section, they say that this V sub C does not have to exceed 0.9 times V sub H. Now remember, V sub H for us is required to be 55 knots, our maximum level flight cruise speed. So you do that little calculation and we come out with 49.5 knots. So this is the number we're going to use since we don't have to exceed this number. Although we will use this number in another spot just because I thought it might be useful. But for us, we're going to assume for most of our calculations, we're at 49.5. Now the dive speed is something very similar, 1.4 times V sub C min. And so here's why I decided to go ahead and use that 68 knots. So we came out with 95 knots for V sub D. We probably could reduce this too, maybe down to something like 75 knots, but I think we'll leave it here for now. Now our last design speed is our maneuvering speed, V sub A. And again, part 23 gives us a calculation for figuring out V sub A. So basically, you just take V sub S and multiply it the square root of N1. And we haven't talked about what N1 is yet. It turns out that's our normal positive load factor, and it's 3.8. So let's go ahead and do that calculation. So 28.6 knots multiplied the square root of 3.8, and we get 55 knots for our maneuvering speed. Well, that's really close to our V sub H. Now keep in mind, V sub A changes with the weight of your airplane. We did this calculation at our maximum gross weight. But what happens if we go to the other end, to our minimum weight? Now remember, we said that was 459 pounds. So I did the stall calculation again. That turns out to be 26.9 knots, and calculating V sub A with that value gives us 52.5 knots. So at our maximum weight, we're at 55, almost 56 knots. At our minimum weight, we're at 52 knots. Now, one of the things that's really nice about this is that it tells us that as long as we're climbing or level flight, as long as we design our airplane right, we can't tear the wings off the airplane. It will stall before that happens. But if we're descending, that's different. Well, now let's talk about those load factors. We just looked at one, N sub 1. So N sub 1 is the positive load factor. So when we're pulling positive G's, this is the maximum load factor that the airplane is designed to handle. And that's 3.8 G's, and that comes from part 23. That's a 3.8 here. N sub 2 is the opposite, or the upside down, or the negative load limit. So when we're pulling negative G's. And that is 1.52. Now the positive load factor is just a flat number, 3.8. The way you come up with N2 is for normal category airplanes. You multiply N1 by 0.4, and that gives you your N2. Now the next N number is N sub 3, and that's a gust load factor. Now generally the gust load factor is going to be just a little bit more than N sub 1, and it applies at your cruising speed. That's where you're supposed to be spending most of your time in your airplane, is at your cruising speed, and you can hit gusts, and that will increase the load on your airplane just a little bit. So generally when you're at V sub C, you have to have just a little bit more of a load factor. But you'll find out for us, this doesn't really apply. But let's go ahead and look at the calculation. So for us, this N sub 3 is 3.45. And then on the negative side, it's minus 1.5. Now both of these are at V sub C, it's just that one is when we're pulling positive G's, the other one is when we're pulling negative G's. N sub 4 is the same thing, it's just at the dive speed. So you have to be able to handle some gusts there too. But the gust you need to have to handle is half of what you handle at the cruise speed. At cruise speed, the gusts are 50 feet per second. At N sub 4, it's half of that at 25 feet per second. Oops, this should be N sub 3 here, not N sub 4. The numbers are correct, I just didn't put a subscript of 3 here. And then N sub 4 at the dive speed, 3.12 positive, minus 1.12 negative. Now if you want to know how to actually calculate the gust load, I don't have it here. Look in this section here, and I did put it here on this next page. Let's take a quick look at that. So here's the next page. Here's the actual equation or calculation, this gust load limit. And here's all the variables. So you can see it's a little bit involved. I don't want to go into all this right now. But here it is if you want to look at it real quick in the video, or look at this section in the old part 23. The last load limit I want to talk about is N sub F. I'm calling it N sub F. And this is the load limit for when you have your flaps fully deployed. Now in part 23, it's just a flat out 2.0, and that's in the positive direction. If you're pulling negative G's, it's 0. In other words, don't pull negative G's when you have your flaps fully deployed. I also did the gust factor for down here at the N sub F, the V sub F speed. And just for grins to see what it looks like, it turns out it's 2.0, which is kind of nice. And that's in the positive direction. And negative direction, it's 0.01. That works out. You don't have to worry about gusts when you have your flaps fully deployed. Well, now that we have all of our load factors and our design speeds, let's go back and look at our flight envelope. On the horizontal axis is our speed. Over here on the vertical axis are our load limits. So you can see our N1, N2, 3, 4, and N sub F. So N sub 1, remember it's 3.8. That's this line right here. Now V sub A, our maneuvering speed, is right here at this corner at about 55 and a half knots. So if we're flying here below the speed of V sub A in this area here, our airplane will stall before we hit our load limit of N sub 1, a 3.8. But when we're flying above V sub A, this line would continue on up. That means we could actually hit our load limit before we stall the airplane. So we could damage the airplane if we're not careful up in this speed area. And as I said before, V sub A and V sub H, our maximum level flight speed, are about the same. So for normal cruise, we don't have to worry about exceeding N sub 1, which would be probably about 50 knots, something like that around in here. So that's fantastic. But when we start diving, let's say we push forward on the stick before we reduce power, we can quickly go up above 55 knots. Now on the negative side, we don't have quite as much margin. So if we're pulling negative G's, we can only go up to about 42 knots before we could start exceeding the load limits on the airplane. In this case, it's about 1.5. Now let's talk about with the flaps deployed in our landing configuration. In that case, down in this area, down to about 35 knots, if we're below 35 knots, the wing will stall before we cause any damage. But above 35 knots, we've got a load limit of 2. So in that case, we have to be a little bit more careful. Now we don't have to worry about gusts because we saw that load that we would have here at V sub F is only 2. So gusts aren't an issue. And by the way, it's not necessarily the wing that's the issue, although I guess I shouldn't say that. The rear spar could be an issue and the flap itself would be an issue. That could be damaged in this area right in here. Now let's talk a little bit more about gusts since we just mentioned it. Our N sub 3 is our positive load factor for gusts, and that was supposed to be at V sub C. If you remember that minimum V sub C that we calculated before, that's 68 knots. This one here, but we know that we don't have to exceed 49.5. But up here at 68 knots, I didn't do the calculation, but it could be very easily that we would be up in this area. And typically for light airplanes, heavier than our ultralight, but for typical light airplanes, it would be just a little bit higher up in this area. For light airplanes, you're typically going to be cruising at a higher speed than V sub A, at least for quite a variety of light airplanes. But for us, we're actually cruising down here below V sub A. And if you remember right, it was about, 3.5 knots, so right up in this area. Now that means a gust could potentially stall our wing if we're already up here really close to stall. But that's 3G, so that's quite a bit of pull on the airplane to start with. Now our dive speed, if you'll remember, that was just a little bit over 3 right in here. Our 3.8 Gs is still above that, so we don't have to worry about gusts up here at V sub D. And the same is true down here on the negative side. Our gusts are a little bit less than what our calculated N sub 2 is, so we're good there too. Now all the loads we've been working on so far are symmetric loads on the airplane. So the load on one side of the airplane is the exact same as the load on the other side of the airplane, whether it's on the wing or the tail or any other surface. And it's at stabilized flight. In other words, we're not pitching up or pitching down or rolling or yawing. But when we are pitching or rolling or yawing or deflecting our ailerons or our rear control surfaces, those are asymmetric loads. So I have to deal with those too. And I'm kind of showing that up here. For example, on the tail, I'm showing how one side can have a different load than the other by the length of these arrows. And on the wing, same thing. When you're deflecting ailerons, you're going to have less load on one side, more load on another side. And gusts can do the same thing. Gusts can create more load on one side and less on another side. So let's talk about those issues. So let's talk about asymmetric loads on the wing to start with. So to deal with gusts, that's pretty simple. You assume 100% of your load on one side of the wing and 75% on the other side of your wing. So it would be N sub 3, our limit factor, at V sub A speed. Another calculation you do that's not for gusts is when you deflect your ailerons. In that case, you use 2/3 of N1 plus whatever load your aileron are going to apply to the wing. Now the ailerons are going to apply 2 different loads. One is going to be lift. Now it could be up or down depending on which direction the aileron's deflected. But it's also going to change the coefficient of moment of the wing. It's going to try to twist it nose down or nose up on the other side. So you have to take that into account also. And part 23 gives you a good way to estimate what the difference in your coefficient of moment is going to be. And that's 0.01 times the angle of deflection of your aileron in degrees. So that makes it really easy. Now your ailerons themselves have to be able to handle a load. So you have to be able to calculate the load of the ailerons at the V sub A speed and 1/3 of the deflection of the ailerons at V sub D. I mentioned safety factor a little bit earlier when figuring out the ultimate factor. Now safety factor typically is going to be 1.5, but there are some exceptions to that, and that would be like on fittings. So you're going to take your safety factor of 1.5, multiply it by 1.15 to get the safety factor to use on fittings. On control surface hinges, it's even greater, which is kind of interesting. They want a safety factor of 6.67. And there are others, but these are really the ones that fit in more with what we're working on. Like there are safety factors for the controls, for the control linkages, and a number of other things. And we'll get to those as we work on the design of the airplane. We spent all that time calculating our various loads and our load limits. Let's actually use one of those right now. So let's use N1, our positive load limit, and figure out what the load is going to be on our wing. I should mention though, when you're doing the load limit for the wing, you don't generally include the weight of the wing in your weight, but we're going to include it here just to make the calculation a little faster. So we take our load limit, which is 3.8, that's N1. We take our weight, and we take our safety factor, which is 1.5. We calculate all those together, and we come up with almost 3,000 pounds positive load limit. Let's do the negative load limit. So the only difference is that our negative load limit is 1.5. We calculate that out and we get about 1,200 pounds. So it kind of gives you an idea of the magnitude of the results that we're going to be dealing with on these limits. I had a whole lot more in this video to start with. I had information on loads on the tail, both the horizontal and vertical. Of course, we got a V tail, so we'll have to do something slightly different. And on the engine and a few other things. But the video got too long to include all those, so I'm going to break up the video a little bit. So we're going to have a video 10C where we talk about horizontal and vertical tail loads, both symmetric and asymmetric. We'll talk about engine loads because that's kind of interesting. And other loads I'll leave for future videos. And that'll be things like gusts when you're on the ground, tie down loads, landing loads, etc. Well guys, thanks for watching. Until next time.